everyone. Can everybody hear me fine?
Yes.
Back there? Yep, okay. Let me know if you can't hear me and I'll try to speak up more. Okay, so to start off, I would like to actually thank the organizers of the Papers We Love meetup for doing such amazing things and continuing this really fun event. Papers We Love is my favorite meetup, so it's an honor and pleasure to be actually speaking here about the things I'm passionate about. So thank you. They did not pay me, but okay, so let's get started. So you may be wondering who I am. I work on search infrastructure, as Ishan mentioned. I work on the scheduling and indexing of the search. That's during daytime, and then I'm a very curious person, so I have a lot of different hobbies. I like to, my curiosity drives me to acquire new hobbies, new skills. So I actually do oil painting in the evenings and archery. And as Ishan mentioned, Loom, which is the graph algorithms and visualization library written in Clojure, for Clojure. So I'm working on that. I'm the active maintainer and contributor. And actually, curiosity is what brought all of us here today. Instead of taking a walk on such a beautiful night, we're here learning about VMs and trying to expand our knowledge. So welcome. One of my biggest passions is compilers. If you've talked to me before, I probably talked to you a lot about compilers, about cool compiler technologies. And the picture you see here is actually of my favorite book. It's called Advanced Compiler Design and Implementation by Muchnik. So if you ever get curious about compiler optimizations, I highly recommend it. It's really, really interesting. So today, the paper is related to one of my biggest passions. It's about interpreters, compilers, virtual machines. And the paper is called One VM to Rule Them All. You may be wondering, why is it called that? It's about one particular VM technology, but why is it called One VM to Rule Them All? So the paper in the related work section actually discusses that there have been an agreement in academia that when you build a virtual machine for a particular paradigm of the languages, for instance, like object-oriented virtual machine that has in mind object-oriented languages, it's very hard to build other languages and have them be high performance on the same VM. So this paper tries to come up with techniques and approaches to bridge the gap, the performance gap, and actually make it work for any of the languages in any of the paradigms. So let's see how they did that. A quick overview of what we're going to talk about today. So first we will introduce the concept of interpreter, compiler, just-in-time compiler, and virtual machine. Then we'll talk about the Truffle Grail, the happy couple that makes up the core of the paper, and how they interact. Then we'll talk about no specialization, which is the technique that Truffle Grail uses to make it work, to make it be high performance for any of the language implementations. And then last, we'll talk about the current state of affairs in the Truffle and Grail world. This is your chance to brag, so let's take a show of hands. Who here is familiar with the concept of interpreters? Great, compilers. Okay, virtual machines, very nice. Who wrote an interpreter or compiler or virtual machine here? Excellent, okay, very nice. Who actually designed the language or attempted to design a language? Very, very cool. And sounds like we're going to have a lot of fun here. And who read the paper? Wow, okay. Woo! Excellent. And who played with Truffle Grail? Well, hopefully by the end of it, you'll be so excited about it. You? Oh, nice. Okay. Excellent. All right, so let's get started. So it seems like a lot of you are very familiar with what interpreters and compilers are, but to make sure that we're all on the same page, we're going to talk about what they are and what's common and different about them. But instead of me talking, I'll let this video tell you about it.
When you land in the world of computers with their strange, convoluted machine language, it's a bit like landing on another planet, whose inhabitants speak an equally strange, convoluted alien language. Getting a mechanic on planet Gobbledygook to repair your spaceship would present the same sort of problem that you have when you want to get a computer to do something. Everything you say has to be translated. And you have a choice between two different sorts of translator. One of them is called an interpreter, and the other is called a compiler. Let's suppose that you've previously written out your list of instructions for the repair of your spaceship. And suppose that you choose the interpreter to do the translating. He reads your first instruction, open lid of rocket engine, translates this into gobbledygook, and immediately passes it on to the mechanic, who executes the instruction. Then the interpreter reads your second instruction, remove spark plug, translates this into gobbledygook, and passes it on to the mechanic, who executes it. And so on and so forth. Now, notice how the interpreter works. He stays with you all the time, and he translates each of your instructions immediately, one by one. This is a rather slow process, because the mechanic has to wait while each instruction is being translated. But, on the other hand, it does give you a chance to correct your mistakes as you go along. If the mechanic removes the wrong spark plug, for instance, you'll see this happen right away, and you'll be able to change your instruction accordingly. Compare this with the way the second sort of translator, the compiler, goes about his work. He takes your complete list of instructions and without further ado translates the whole lot straight into gobbledygook. He then hands them back to you and goes away, leaving you all on your own. All this has taken some time, but from now on things will go very fast. You hand the complete list of gobbledygook to the mechanic, and he executes them all in one go. Bang, bang, bang. There's no waiting about this time. But there's one disadvantage to this, of course. If there was a mistake in your instructions, it's too late now. This analogy comes very close to the way the interpreter and compiler translator programs actually work with computers. An interpreter runs slowly, starts right away, and lets you see how things are going. Whereas a compiler takes extra preparation time before your program can run, but then lets it run very quickly and efficiently. To help you remember the difference between an interpreter and a compiler, look at the words themselves. Inter means between. The interpreter is always between your program and the computer, and it translates line by line. To compile, on the other hand, means to pile together. A compiler piles together your entire program and translates the whole thing all at once. Which one you use on planet Gobbledygook is entirely up to you.
Alright, now that we know how interpreters and compilers work, let's talk about them on examples. And my computer froze.
Using an interpreter or compiler?
Oh,
Literally compiler. Let's see. Alright. Okay. Here we go. So, what we see on the slides is the abstract syntax tree. Is everyone familiar with that? Well, we'll get started. So, suppose we have a function, expression which is 2 times 11 plus x. The way we would express that in an abstract syntax tree form is 2 times 11, and the result of that you add x. So what the interpreter will produce to you is something like multiply 2 and 11 and store that in a temporary variable. The reason we want to store it in a temporary variable is because we want to use the result of multiplication later on. So then we walk up the tree now. So we visited the multiplication node. Now we walk up the tree. Now we need to load x. The reason we load x is that this value came from elsewhere in the program. Maybe it's a user input. So we need to access the value of variable x. And now what we're going to do is we're going to add temp1 and temp2 and produce the result. For those of you familiar, this looks more like instruction, but I'm avoiding the 3-argument instruction tab just to make sure we are all on the same page and it's not too confusing. So interpreter will produce this every time it visits a node, whereas the compiler will walk the abstract syntax tree, generate to you the program, produce these instructions all at once. Are there any questions on this at the moment? Okay, and feel free to interrupt me if you have any questions, or just raise your hand and we'll make sure to address them as we go. So now, JIT compilers, which are set for just-in-time compilers, the way I see them is that they are interpreter combined with a compiler. So first, JIT compiler starts out in interpreter mode and runs the program, and it tries to detect if there are any code paths that it executes more than once. And it defines some threshold, suppose 10 times. And if it executes function more than 10 times, then it will compile the function and then run the compiled version of it on the next execution. So first, the just-in-time compiler runs it in interpreter mode, and then for the hot paths, for the code paths that run more frequently, it will compile them to be run faster. The name comes from just-in-time, so as it detects that the code path is being run very frequently, it will compile it just in time for the next execution. Are there any questions about this? All right. Let's talk about virtual machines. So in a C program world, in a C world, what we have is we write a program. So this is C compiler. Can also everybody see my writings? Okay. So we compile it, and then we produce machine instructions. So this would be your x86 instructions. Now, with the virtual machines, what we do is instead of compiling directly to machine instructions, we'll take the program, and then we'll compile it to bytecode. And then the virtual machine will interpret bytecode to machine instructions. So why should we use this level of indirection, compiling first to bytecode, then to machine instruction? Isn't the whole goal is to eventually compile our source code to machine instructions? Well, there are two advantages of doing it this way. One of them is that you're able to, with the same program, you're able to target any hardware. So the same Java program that you read is able to run on your laptop, on your desktop, on your mobile phone. The other advantage is that it's easier to optimize bytecode. So you may be familiar with LLVM, the low-level virtual machine. Yeah, so it's much harder to actually optimize machine instructions. And there are many reasons, some of them being that with the hardware, we have limited number of registers. We have limited number of memory. So when we compile code, we have to work around those constraints. Whereas when we compile to bytecode, bytecode assumes a limited number of registers, a limited memory, and we can do much more sophisticated optimizations before we compile it, before we interpret it to machine instructions. So this allows us to do many powerful optimizations. Okay, so are we good on virtual machines and where they stand in the whole chain? Okay, excellent. So now let's talk about Truffle and Grail, which make up the core of the paper. So Truffle is a language implementation framework. So to break it down, framework means API, so it provides to us some functions that we have to implement in order to get the functionality that the Truffle API has to offer. Language implementation stands for language design. If you have a new idea for the language you have and you implement it using the Truffle API, then you'll be able to have an implementation of your language. And Grail VM is an extension to Hotspot VM, but it exposes Hotspot VM's internals. So Grail VM is an implementation of Truffle API that uses your language's implementation and compiles it using Grail VM. Okay? So where does each of them fit? So Truffle is for writing interpreter for your abstract syntax tree. And Grail is that gives you JIT compiler for free. As a language designer, you don't actually need to know how Grail VM works, how to make it work. All you need to know is how to implement your language using Truffle API, and that's it. So the beauty of that is if you're really into a type system and you came up with a beautiful way to represent type system, or you figure out a beautiful way to represent complex computations, or you came up with an interesting syntax and you want to try that out, this allows you to not get bogged down by code generation or compiler optimizations to get much performance out of your new language, but instead focus on the design parts of the language. So you can get started with writing programs in your new language as quickly as possible and iterate on it without having it be too slow. So how does Truffle and Grail achieve that? Well, it achieves that with several different techniques, but in my opinion, the most important one is node specialization. So let's look at what it does. For now, ignore the right-hand side with a second arrow. We'll talk about that in a second. So recall our program that we had, the 2 times 11 plus x. So actually, the abstract syntax tree that we had written is very similar. It looks very similar to the one we have on the slide. So we have our plus x multiplying 2 and 11. Okay, so first let's look at the node transition. So before we start evaluating our program, we don't know the types of nodes that we're operating on. We don't know the types of our inputs. We don't know anything about it. So it's uninitialized. All the nodes are of an initialized type. And we see the node transition. This is just an example. So for multiplication, for instance, you may be operating on integers, doubles, maybe strings if you define multiplication as a way to concatenate strings to both, and a generic way to do multiplication or naming to objects. So now you can go from uninitialized to integer, double, generic, or string, and you can, if you overflow the integer, you could actually go to either double or generic implementation. So at this point, 2 and 11 are both integers. So now the multiplication actually is done on integer type. So we expect integer as our return type, and we expect that the multiplication is integer multiplication. So what we can do is we can actually swap out those nodes and specialize them to be of integer type. So now, as we're evaluating the program, we'll replace our nodes to be integer types. And because Truffle assumes implementation in Java, it will probably be something. It will probably look something like this. So it will be like public and multiply ints, and it takes 2 integers, int x and int y, and then it returns the result of multiplying x and y. Okay, great. And now we'll have a profiling feedback in place for us. So we'll have a counter that counts whether we exceeded the threshold. And when we do exceed the threshold for being how many times they got executed with input types being integers. Once we exceed that, we will decide that we're probably in a stable state. We will speculate on that the user will not give us any other input but integers. So now we can do partial evaluation, which is on the right-hand side. So on the high level, the way you can think about partial evaluation is, for instance, on this example, we have 2 times 11 plus x. So really what the program is 22 plus x. So what we're doing here, for those of you familiar, is constant folding. And constant folding is just a special case of partial evaluation. So we don't know what X is. We have to get that at runtime. But we can do something about other inputs that we know. So our interpreter does no specialization. Imagine if it didn't do no specialization. It would behave just like any other JIT compiler. Now, because it does specialize on our language and our inputs, what we can do is we could compile that part of the interpreter away. So if, from the perspective of the hotspot VM or Grail VM, we have our application code, like the source code, in the new language, and we have an interpreter code that's running and interpreting and does the no specialization. We know what the interpreter does, so we can compile that. That is partially evaluated. Does that make sense to everybody? For the origins? Okay. So now we have our compiled code, we're running, we're happy, and now we're much faster. But what happens if, instead of getting here 11, we actually get 0.1 elsewhere? Elsewhere in the code. Or this was just a variable. So what we will get is, so what we'll get is, we'll get a double, and we can no longer use our integer multiplication, the assumption that we made that we'll be operating on integers only. So what we have to do is we have to deoptimize. So we'll fall back to interpreter. We'll fall back to our abstract syntax tree. Now, instead of having integer on the right-hand leaf, what we're going to have is a double. And now we perform multiplication on doubles. So it will be something like public. We expect that the return type will be double. And then multiply doubles. Double x, double y. And then you get the idea. Yeah.
Specialization makes perfect sense. I didn't consider the constant specialization fits in. Obviously, you're not going to write a multiply 2 by method. Is it taken care of because JVM takes care of it, or is it?
Right. So suppose we had this tree and it was still 11. So really, what we worry about here is this node, right? What type of input does this node operate on integers before, right? So we'll specialize this node. These coming is just an example, like a particular example of inputs, but it could be other arguments coming from elsewhere. Okay. All right, so now we're back to it being 0.1. Obviously, we can't perform integer multiplication on a double and integer. Correctness is really important to us. So we will, oops. I'll learn how to use this clicker by the end of the talk. Okay, so now we have our double. Now we will continue running our program with the assumption that it will be double multiplication. And when we exceed our threshold, for instance, on the 11th time we decided that it's actually multiplying doubles, what we'll do is we'll agree that we are in a steady state and recompile this again using partial evaluation, but now with a double multiplication as the type of the node. Yeah?
So what happens if you thrash between types? Does it create two specializations that we'll use?
Good question. I'm actually going to cover that in just a moment. But if I don't answer your question, let me know. So yeah, so actually, good question. That leads me to it. Suppose you had a function that is full, and we'll assume dynamic types, and it does something like a plus b. Now we have three call sides. S is equal to full, 1, 2. Y gives us inputs doubles, and at call side Z, we give it strings. So the hello, the WM. Okay. So as we, in the abstract syntax tree, in the interpreter, there will only be one tree for food. So as the 3 different call sites code with different types of inputs, what we're going to have is they're going to be poisoning each other's profiling feedback. And in the end, we'll end up with generic implementation, because if you recall the state transitions, we'll go from integer here to double, and then we'll get the string, so we'll just go to the generic implementation, which defeats the whole purpose of doing node specialization. So instead, what we're going to do is we're going to use the technique called tree cloning. So for each call site, we're going to clone the tree, abstract syntax tree, for the function foo, and we're going to insert that there. Now, as long as at this call site we keep calling it with the integers, we will specialize with integer addition. And at this call site, we'll specialize with double addition. And this call site will specialize with string addition. Yes?
So you call that tree cloning?
Tree cloning.
Tree cloning.
Yeah, cloning of the trees, yes.
And that's a space trade-off?
Yes, so that's a space trade-off, but the advantage is we get to use action node specialization and produce optimized code. Yes? Oh, sorry. Go ahead.
So is node specialization kind of skipped in more strongly typed languages, like say Haskell or something, where it just knows from the program already what the types are?
It could do that, yeah, definitely. This is. Sorry.
Okay. So this is strictly about dynamics.
Is that no, that's strictly.
That's their, that's their use case.
Well, those are the hardest.
Because there's a whole range of from dynamic types to showing type languages, so.
But even if you're working in a statically typed language, you have now required types.
Yeah.
Right, so you can still specialize.
Yeah.
In the actual use.
There's some really amazing work that's been done on doing JIT specialization in type languages. It's just not used that much, but it works really nicely.
Go ahead.
So is tree cloning like a fancy term for like function inlining, basically? Like in this case, it seems like what you're doing is you're inlining. Like the reason you have to clone a tree is because your abstract syntax tree belongs to a function definition. And so you're talking about call sites, so it's like you're inlining the function first, just tree cloning, and then you're optimizing each inline.
Almost. So it will potentially become inline. The function will potentially become inline later.
I see, okay.
But it's still going to be call function until it gets optimized.
You can clone for different reasons. So you can clone to specialize for a call site, or you can also clone to specialize for a code path at a common call site, or et cetera, et cetera, et cetera.
So like a code path in a loop, for example.
Yeah, like you might have a loop where it goes through 2 code paths regularly. You might specialize it twice. So you make 2 clones, 1 for each unique code path.
Okay.
And then later it will be inline if it's been called for long enough, or if the compiler decides to do global optimization, it makes sense for it.
Okay.
Yes, go ahead.
Is there a threshold for cloning, or does it clone as soon as it sees different values?
So I believe that's actually something you can do with Truffle API. You can determine yourself. Yeah.
Okay.
Yeah.
Is there a cost to dispatch, or does it really not matter because the JIT is tracking usage anyway? So it kind of.
So I don't think there is. So if I understand your question correctly, you assume there may be a cost to dispatch because now you have to call elsewhere.
You have
well,
to decide which streets to.
So there shouldn't be any extra cost to dispatch because you're just cloning it over. You'll still be calling that function even if you didn't do tree cloning. So what this allows you to do is specialize better, depending on the call set. Any other questions? Yeah?
Do you have to predefine all of the dispatch types ahead of time?
Yeah, that's actually something. So you have to define how you will specialize on the nodes, all the different.
Do you have to
Yeah.
define like a DAG associated with type specializations?
So in the paper they have examples. They have a DSL that makes it look pretty easy. It doesn't seem, it seems like the DAG is, at least in the simple examples, implicitly derived for you.
Yeah. So actually, so you use Java's annotations to do that, which is makes it like very seamless, little domain-specific language to do that. And the interesting thing that they do is they use exceptions for control flow, for non-local control flow. So for instance, for integers, if they overflow, then they know they need to be doing operations on double. So they'll throw an exception and then catch that. But you describe that as different functions. And the function that specializes in double just catches the arithmetic flow exception and continues on. Yeah?
So how much of the node specialization that's done is automatic and how much needs to be described by the language?
So you as a language designer only know what makes sense in your language. So you have to do all the node specialization yourself and define it.
It's primarily providing you assistance in like profiling and like actually maintaining it, like provenance of like where data comes from. It's doing all the bookkeeping for you, but you actually have to specify the optimizations for your language.
Okay. Good. Were there any other questions, Sarah? Oh yeah, sorry, go ahead.
Yeah, I'm not familiar with the compiler technology, so I just want to clarify the concept. So let's say this is a JavaScript expression, 2 times 11 plus x.
This one?
Yes.
This one?
Yes. This is a JavaScript expression.
Okay.
I implement interpret this Java. So what do you mean compile this? I understand how I interpret this stuff.
How you would compile this stuff?
Yes, when you say this expression get compiled, what do you mean?
Okay, so if
do you code Java program? Is that what you mean?
So by compiling this expression, what I mean is that you would take this expression and then possibly do optimizations like we discussed. You would turn actually that into 22 plus x and then spit out the machine instructions.
Yeah, actually that's right. Is it a bytecode in Java program?
So
you produce Java program, you produce bytecode. Right.
So you write. So in Truffle, you write Java program that describes how to interpret your language, and then it gives you compiler for free. Okay. Mm-hmm. All right. So. So you may be wondering what kinds of languages are there. At the beginning of the talk, I mentioned how the author set out to build the VM that is able to deal with different paradigms of languages. So there is JavaScript implemented, Ruby, Python, R, and J. And the paper actually talks about some of the challenges and different techniques that they used to interpret each of those languages. I highly recommend it. The sections are very short. We could also discuss it afterwards if you're curious. So now let's talk about everything, all the useful links that you might care about if you're excited about this. So there is the Grail on OpenJDK. So it's part of OpenJDK effort now. And you can find all the wikis for the Truffle API, for Grail VM. There is a Truffle Ruby effort, and there's actually a very interesting post about how they made Ruby work on Truffle Grail platform. There is a fast R, so a fast implementation of R. Zippy, which is an implementation of Python on Truffle Grail. And there is Truffle Sum. So Sum is a restricted subset of Smalltalk that is used, I think, primarily by research community to develop, to do research on VM design and VM technologies. So it's very interesting. There's a lot of work being done. The authors continue to do work. So on system modularity, you can find some slides. Don't worry about recording these links. I'll post the slides online so you can get access to them. So for system modularity, it's actually interesting in that they were able to scale up the team from 1 person working on this project to 50 people working concurrently on different parts of the project. And some of the examples of modularity, well, they took the Grail VM, and well, Grail VM could target different architectures, right? It could target different host runtimes, host VMs. So expanding into all those dimensions. I think they're launching it soon, or they already launched it. The website, it's all the things Truffle and Grail. So all the research that is currently ongoing, all the papers are being published to one place, which is grailvm.org. And actually, the small talk implementation in Truffle Grail is the fastest now, and you can read about it, how it compares to other implementations. There's also being significant progress done on R, Python, Ruby, and Smalltalk. Are there any questions about this so far? Yeah.
So I guess this may be a very naive question. So what is the core innovation? Is it that the ability to describe these transformations on ASTs that are kind of language agnostic? So that's the big thing.
Yeah. Are you familiar with PyPy by any chance, or IPython? Okay, so it's a similar idea, right? So PyPy is the Grail VM equivalent, and RPython is the Truffle API equivalent. The difference between them is that PyPy and RPython are give you the tracing JIT, whereas this gives you AST JIT compilation. So, and it's more powerful because you're operating on a higher level, so you can infer a lot more things from the semantics of it and do many more optimizations, because now you can do global optimizations on the whole tree as opposed to just on the particular trace. Yeah?
Can you talk a little more about trade-offs between PyPy and Grail and
Sure. I mean, so RPython is a restricted subset of Python in which you describe how to implement your language. Perhaps you notice somebody is more knowledgeable than I am. I haven't played with it at all, but the main difference is that the tracing JIT versus AST JIT. So is everybody familiar with what tracing JITs are? Okay, no, okay. So basically what you define is you define entry points and exit points from traces. And traces are just a sequence of instructions that runs one after another. So if you had some sort of control flow like this, and then you just have a bunch of nodes, this would be one trace. So you could execute them. You could speculate that this is you could speculate that you always take this path because of what you saw, and then you would just compile the whole trace. Yeah.
So those circles are supposed to represent conditional branches.
Yes. So the branching off is the conditional branches, and these following is just consecutive instructions. Okay. Yeah. Go ahead.
So I didn't read the paper. So
yeah. Sure.
It's good to admit it, though.
It's good. You said that using Truffle, you describe how to interpret your language. So I'm assuming that means like there's an API for like giving semantics to your language. Is that like what Truffle does?
So you define semantics, right? So like with no specialization, for instance, you define that the addition node, how that should be executed, how to specialize in the types.
You're actually writing execute methods on a dynamic subclass of expression. So you're implementing like a virtual dispatch table, and then you're defining a bunch of different specializations, and it's analyzing your classes, and it's building dispatch tables and stuff from that. So you're actually writing an interpreter that's an AST interpreter.
Okay, so there's like a dynamic value type or something.
Yeah, so everything's like expression.
Oh, I see. And you just return an expression.
Yeah, but so like you write execute, and you also write execute int. And you'll say execute int is the version of execute when I know my return type is int. And so you say, when I can execute object, I switch. And then you say, well, if I know my return type is int, then I can bypass the call to execute and just go directly to execute int, which means that the caller has to know to go to execute int directly. So you're writing an interpreter, and then it's a framework that takes that interpreter and like chops parts of it out for you statically while you're running through.
And you can specialize on the arguments too with expressions?
You can specialize on more or less anything.
Okay.
But you may have to specialize and specialize or do so.
Okay.
So if internally everything is objects or objects of particular types that you're interested in, and you're interested in dispatching on particular types, particular prototypes, you could express all that using Truffle API. So for JavaScript, for instance, they define this notion of shapes because it's prototypal based.
Yep.
So if something implements this and this prototype, then it requires a particular shape. And then you make an assumption that everything that is of particular shape can be executed using the exact same function.
Okay.
Okay. Is that more clear? Yeah. Okay. Okay. Yeah. Go
This
ahead.
question is probably coming from the naive corner of things, but would this be useful for designing a functional language? It seems very object.
So good question, right? It's actually something that they're very much interested in, and I'll talk about in a moment about the work they do to enable expressing functional languages using this framework.
This seems kind of similar to Scala's implementation a bit.
Okay.
Yeah, I look very limited knowledge, but.
Okay.
So they talk a lot in the paper, or at least their example in the paper about JavaScript, but I don't see that in their list of things that are actively ongoing.
Let's see. So
It's called Nashorn.
Nashorn. Okay.
Oh, I know it's Nashorn. So cool. That's cool.
Okay. Yeah.
So in implementing your language as an API interpreter in Java, I guess you're kind of, is it true that you're kind of bound to the Java VM that you're working on understanding of things like garbage collection, right? So I guess my question is, I want to implement my own language. Can I, and I want to use Truffle, can I do this and also implement my own garbage collector, or do I have to use whatever Graal provides as a garbage collector?
So very good question. So what you can do is you can just use just the Truffle API and use any VM that you want. Now, the advantage of that is that you don't have to use Graal, right? The disadvantage of that is that Graal VM speaks Truffle API, so you won't be able to leverage the potential that it has because other VMs would not understand the Truffle API, would not know how to optimize it. But then you get your freedom from Graal VM. The other thing is that they are doing research into making a lot of parts of the system swappable, modular. So who knows, maybe that's also something that they will implement where you could just plug in your garbage collector and play with it inside the Graal VM.
So can you when this program is running, you could still tune the GC of the JVM that the Graal JVM is running on top, right? Or not?
Seems like you have as much control as Java do.
Yeah, so you still have the opportunity to run your programs and see what their working profiles were, and I mean, I could see that being, if you're interested in a programming language where there's some tighter interaction between the garbage collector and the semantics of the programming language, then that would be like more of a challenge, but hopefully
yeah, it could be like implement a reference point language or static LPT language.
Yeah, or I was thinking of something like a Erlang VM that had an isolated stack so that you would have different guarantees about the semantics related to memory collection. But I think this obviates a lot of the need for that. Ideally, you wouldn't ever have to tune your GC or those GCs.
Cool.
Okay, yeah.
So you have the AST, but you also have like state, right? Like you have variables all over this.
Okay.
And like, does it sort of keep everything in memory, like in the most general type, and then when, right? Like if I have, for example, like if I have some variable, right, and like I went through some code path and I know it's an int, right? Like, but now I'm not in the AST anymore. Like that int is like in the memory location. Like eventually I like load that again, right?
Okay.
Somewhere. Like, does that, you know, like, how does that work?
Okay, sure. So when you're interpreting, when you haven't compiled it yet, right, and you probably, that's when you don't know what your types are yet, right? It would do the checks of types, right? And it would figure out what to specialize on if it can.
Okay.
So now, I'm not quite sure what you mean by having them in memory and not knowing.
So like, if you talked about JavaScript, so like here's an example, like I have a global variable, right? And like in JavaScript, like I could imagine where, you know, like everything is, you know, a JavaScript object, which is very general, which is not optimizable. But like then maybe, you know, the AST, like I put this thing in here and the AST figures out that like you know, the AST compiler figures out that, oh, it's an int, like, and then I could like make this path like int specialized, right? Then like once I write that back to like some variable, I don't really know what type that variable is necessarily, right? Because then that's not talking about the AST, but it's talking about like the actual object graph.
Okay.
Yes.
So when you specialize on the node, you also know what the return type is for your node. Right? So like when you decide that you're operating on 2 integers, you will swap out the node and specialize, and the return type will also be integer. And that's also something you define with the Truffle API, what the return type will be.
Okay, so specialization happens after the interpreter, like
As the interpreter is
interpreted, specialized if possible, continue to interpret, continue to interpret, continue to interpret.
Exactly.
But the specialization is all your responsibility.
In Truffle.
So the Truffle API has like a frame object that represents JVM stack frames, and so it's basically assuming you're going to use a JVM like VM representation. And so what will happen is when you program your interpreter, you program it against this frame API, and the Truffle engine knows how to look at your code and see when you're reading and writing to those types and specialize in that to the particular architecture you're operating on. And so when you read or write to a mutable array that's part of a frame object, it goes, oh, that's actually a stack frame. And so it can actually inline all of that and specialize all that to a particular CPU architecture. And even though it looks like you're dealing with like a JVM object that represents a mutable stack frame, in reality that's going to just get all eliminated by the framework. And the result will be like direct loads and stores from the stack.
What if it's a heap object?
Similar mechanisms, but the idea is that you're operating on a virtualization of the garbage collector, of the heap, the stack allocator. Like you have an API as part of Truffle that represents the concepts in the VM that the Truffle engine knows how to eliminate. And that's you can look at the PyPy stuff talks about virtualizables and something else, but that's the same idea. Is that you have an object that does not actually exist after compilation that the code interacts with.
Also, simple primitive values are just stored in a Java primitive array in memory. Like, so instance stuff, there's like Grail has like a couple of long buffers allocated memory just stored there so they can be unboxed. Like when you know the types of you're storing back to like the unboxed array primitive. Nice.
So also for local variables, as Brandon mentioned, with frames, so you want local variables to be accessed to have fast access, right? So first they're represented in an array of local variables, and then as it figures out your pattern of usage and access, what it will do is actually strip that away, do escape analysis to figure out what the accesses are, and that it doesn't go beyond this function scope or something, and then it's going to convert that into normal variables, into normal local variable accesses. And then suppose that it decided that it speculated wrong on that it's a local variable or on the shape of the object, then it has a way to reconstruct the frame back, to deoptimize and store some metadata to figure out what belongs to what, and put all the local variables back into one array and then try again.
Yeah, in PyPy or in Python, there's a function locals, which just gives you a dictionary of the local variables. And as you can imagine, this is slow. And so if you are using PyPy and you call locals, right, it's even more slow because you have everything written compiled, and it's like, oh, actually now this person wants to pretend that they have an interpreter. And so what it has to do is it has to like look through your stack and like undo the work it did to speed you up, and then push that into a map. Whereas in the traditional C Python interpreter, it just gives you a pointer in the current locals collection. So you have this risk that if you operate on the virtual version of what the VM is doing, there's this risk that if it ever escapes, like you actually are worse off than if you had started as an interpreter and assuming you're interpreting. So the API they expose to you is one that discourages you from making that error.
Is there any feedback?
I'm not 100% sure what
so like
facilities
if
they
the JIT
provide.
does escape, maybe it could communicate back up.
Yeah, I don't know.
Any feedback for?
Between the Grail and like the interpreters. So like if you did have like an escape analysis event, JIT would it interpret, pass that back, and then change your.
So it does have, right? So it does have the guards in the code. So when it generates the code for the interpreter, it generates the code to make sure that the assumptions are valid before jumping into it, and then that's how it knows how to deoptimize. Okay. So new features are being added to Truffle. One of them is on-stack replacement for loops. Imagine an example where you have a really long running loop and it's only ever executed once. Well, what a normal JIT would do is it would see that the loop is being executed many times, and it would decide that it will compile it, and it compiles it. But the loop is only ever executed once. So this compilation never gets used because it gets compiled after the loop has finished. So now with on-stack replacement, it solves the problem where the loop is running, and now it figures out that the loop has been running very frequently, and it swaps out immediately for the compiled code. So the loop continues running on the next iteration in compiled mode. So that's pretty cool. Another optimization, another feature they're adding is support for tail calls, which is especially for questions for functional languages support. Very exciting, yeah? All right. So for Grail.
I've seen the other side. I may not get there with you, but anyway, sorry.
So Grail VM binaries are available here. Remember that thing we were discussing, how you don't really have to use Grail VM? Well, if you wanted to use Grail VM, you can actually use it to execute your Java binaries for anything. And they have been working on improving performance for it, and they've seen that it's faster on some workloads. So have fun with that. And I promised on Twitter that I'll say something really exciting for Clojurians. I haven't forgotten that. So the author's actually very interested in Clojure implementation on top of Truffle Grail, and they believe that they will be able to support tail calls, and they'll be very happy to support their efforts on implementing open source Truffle Clojure. With that, I'm going to open up the floor for more questions, if you have any. And yeah, go ahead.
So I was kind of disappointed. Oh, so the paper's awesome. Obviously, it's a great technique. But I was a little bit saddened that there was no experimental results presented. So for instance, even breaking down the type specialization. So for instance, I co-authored a paper in CGO 2010 where we did this sort of type specialization on a graph of the program for the Lua language. And we found like a 2x improvement over like native interpreter speed.
Oh, cool.
So it would be awesome if the authors like presented in a follow-up paper some experimental results.
Yeah, I would check out actually the grailvm.org. They may have papers, I'm not quite sure. They have a lot of papers there, but yeah, they may have more following work describing performance. Okay, any other questions? Who is excited now? Yeah, go ahead.
I'm not familiar with how Clojure is like compiled interpreted now. Like, how would this differ from how Clojure works?
Okay, so Clojure right now is implemented in Java. And there's an effort being made by the community to have Clojure in Clojure compiler, so bootstrap Clojure.
I see.
Yeah, so
statically compile it.
Okay.
Is the answer.
Okay. So who's now excited to implement their own language in Truffle? All right. All right. I think there were a couple questions. Yeah, go ahead.
Yeah. So there was some mention in the paper of something called a polymorphic inline cache.
Yeah.
I'm
Yeah.
not a VM guy. I can guess maybe what an inline cache is.
All right.
What makes it polymorphic?
Okay, so let's talk about that. So monomorphic, polymorphic, megamorphic, right? Monomorphic one, polymorphic few, megamorphic many. Okay? So now specifically let's see. Well, suppose you're in a language with protocols, and you have a protocol foo. I'll call it ifoo for interface. That's like a more Clojure thing. Okay, so now we have A implements ifoo, and we have same with B implements ifoo. Okay, so now foo has a function in it, just one function, say bar. And now A provides an implementation of bar, and B provides an implementation of bar. Now, when we have an object, an instance of one of these, say we have an X, we need to figure out which of the functions which of the implementation we're actually going to invoke, right? So what we're going to do is we're going to check, oh, is X instance of A, or is X instance of B? And then if X is instance of A, then we're going to invoke A's implementation. And otherwise, we're going to invoke B's implementation. So it's not really a cache in the classical sense, like somewhere in memory, key value store. It's in the code, usually as part of the instructions, and it just figures out which of the implementation needs to invoke. So that's what polymorphic inline cache is.
So it's like a dispatch table for claims of type ifoo.
Mm-hmm. Yeah, exactly. And like inline part is like it being just integrated in the code. I think that's what it stands for. Yeah.
Specifically at the call site.
Sorry?
Specifically at the call site.
At the call site. Yeah, yeah. Mm-hmm. Okay. Yeah. Go ahead.
I guess I have two kind of speculative questions. If nobody has those questions. So the goal here, or at least one of the goals here, is to have a VM that is capable of implementing many different varieties of languages on top of it. And I guess I have questions about two families of languages and whether they would be reasonable to try to implement on top of Truffle and Growl.
Mm-hmm.
The first is, so your ASGM interpreter takes this frame object that somehow lets you store local variables. What if I was implementing a language that doesn't have local variables, like a stack-based language, like Forth or Factor?
Mm-hmm.
Would that be possible? Would it be reasonable? Would you still get the same ability to optimize that you get?
Good question. So for stack-based languages, my guess, and feel free to jump in and suggest your ideas, is that you could leverage the frame objects inside it to access the variables and manipulate them. Now for other things, I'm actually not sure. Does anybody have any suggestions?
Did they implement J on Growl?
Sorry?
J is stack-based language? I'm curious. I thought J was
They
stack.
did
They
say
have-
they were
Yeah, they did,
J.
yeah.
So I don't know what the J is stack-based.
So what makes
If
a
you imagine
stack-based
a stack-based
language is that it
language,
has
what you
two
can do
stacks,
is,
not it has one stack, right?
Two people.
So what you can imagine is if you have this function, right, that when you're compiling it, you can figure out, am I popping things off of the stack that I expect from somewhere else, in which case that's like a global, and am I popping things that I can trivially prove I just pushed onto the stack, in which case it's like a local. So you can end up with this, so a stack-based language, although semantically is stack-based, doesn't actually end up that way. Just like, when you write, Java, it's semantically everything is in the heap, but actually it moves things on the stack when it feels like it, and in the runtime it tends to take liberties to make it go faster.
But like, I would have to do that, kind of figuring out where my stack-based indices turn into local variables myself in my implementation. I don't think Truffle would do that for me. Is that right?
Right, yeah. I mean, if you wrote it naively where you're just like, here is one giant list and I'm going to only push and pop on that, then Truffle's not going to be able to do. I mean, you'll get the standard, optimizations that Java and the JVM can try, but if you want to make it better, just as everything with Truffle Grail, the idea is, you have to figure out how to make that, and it'll make it go faster for you.
Okay.
Yeah, I don't know. I'm not totally familiar with Truffle's like call stack, sort of like what provides for debugging and whatnot. But like kind of the defining characteristic of like a Forth or a Factor is that they have two stacks at least, separating data and callback and calls. And so the interesting thing is that you get a call stack somewhat for free in your AST. Like if your language doesn't actually have function calls at all, right? Which is actually totally possible, right? Like you can just inline everything, right? Just insert it, and you never actually like put a named call frame on the stack. You're still going to get the optimizations from the way the AST works, and your interpreter is still going to have call frames in when you call execute on a sub node or a otherwise related node. And so the frame bit is about data on the stack. And so I don't know specifically the answer like what the API looks like, but I know that the interesting thing about stack languages is that they separate the data stack and the call stack. And the frame object that's in Truffle is got an array for the data, and then it's a like linked list essentially for the call stack. And so you can work with them independently, maybe with some trickery.
So this is a core question though. This goes to the core of the paper. Like what's interesting about this? Lots of different languages have been written against many different VMs. It's not surprising, it's not that innovative. What's innovative about this is it's giving you a strategy for implementing a language against a VM. So you don't have to go to the Erlang runtime or the JVM or something else and say, what the hell do I do now? You have the API, which gives you an approach to take. So if it doesn't handle stack languages, I'm sure they're very interested in that insight, and they'd love to add capabilities to support that.
I think even more than that, it provides an opportunity to target a highly optimized VM, which you never have as a language designer. It takes over a decade to optimize it, so you have access to that. And the second thing is, when you agreeing with what you said, it focuses you on the AST rather than the bytecodes, which, as Aysylu said, is a higher level representation, and it's easier to write that stuff.
Well, right, but doesn't everything go to the more abstract as your tools become more capable?
LLVM.
I mean, sorry, go ahead.
LLVM might be a counterexample of that because they optimize on SSA bytecode.
Okay. Well, there'd be two different approaches then. So Mr. Bernstein can talk about the anti-approach of the bytecode versus the AST.
And actually, Truffle Grail authors, the way they compare themselves to LLVM is that they're high-level virtual machine versus low-level virtual machine. If any of you actually tried targeting LLVM, there's a lot of mind-bending you have to do to make a language target LLVM. And then it does all these wonderful things if only you actually get through the pains of making it be represented in LLVM.
So sort of one other thing is that if you're doing specialization, partial evaluation, inlining, all that sort of stuff, you can actually have multiple different VMs, right? So if you have a minimal instruction set, so let's say you're doing a stack language or you're doing a small list, you've got 8 or 9 primitives. You write your interpreter for your 8 or 9 primitives. They have an interpreter for the JVM bytecode. And so what happens is you don't have a bottom to your language. You can just add whatever other nodes you want to the AST, whatever makes whatever optimization convenient. So what's actually happening is that it's going to you're going to write specializations for your language primitives, and then you're going to write compilation to some other set of AST nodes that somebody else is going to have written specializations for. And so if your goal is, and so what's going to happen is if you produce in a compilation step JVM bytecode, it's actually going to execute abstractly, partially evaluate the JVM bytecode before that ultimately becomes machine code. And so there are many, many levels, and what this does is because you have some type expression that has some method execute that's virtual, you have an open, extensible set of things that I know how to interpret in terms of other things I know how to interpret. And ultimately, you're going to keep expanding until you hit x86 or whatever. And so you can actually JIT right through 3 different languages.
So actually, in later parts of the paper, actually, they explained you can't actually do that dynamically. You have to define everything up ahead.
Oh, really?
Yeah. There's another thing that this paper doesn't go into that you can look up later. But if you look in the real research, you'll find it.
I'm operating backwards from the Scala guys, and theirs does that.
Yeah. So yeah, basically you can't. In many cases, you don't end up with a full JVM after all this is done.
Okay, interesting.
Was there? Go ahead. Did you have have a question? Or?
You said you don't end up with a full JVM after all this is done, so they're optimizing away parts of the JVM. Is it?
Yeah, there's a third companion technology that actually optimizes away the JVM and gives you this like
strip down.
Yeah, strip. So the compelling use case is like, you know, man, the JVM is really fast, and man, I really wish this JavaScript is faster than Node, but the JVM takes 5 seconds to start up when I load like a crap ton of code to make it fast. Like, what do I do? And so there's this third thing called Substrate, and Substrate makes it so that you can have like 2 milliseconds to get your JavaScript VM, but in doing so, you give up the JVM fast.
So you lose like stuff like dynamic code loading and stuff?
Yeah, you lose, it's all the dynamic code loading and all the, like, a lot of the flexibility.
Okay.
Yeah.
Did you have two questions?
My next question was, okay, so the answer for stack languages was like, maybe, probably. What about logic programming languages?
They did Prolog.
They did Prolog?
It's
cool. So I guess the answer is yes. I should take a look at that.
Okay. Any other questions, comments, thoughts? Yeah.
Not a question, but
yeah.
Somebody brought up LLVM before, which is really interesting technology too. Something worth pointing out here is that Truffle is doing some things that you cannot do in LLVM that are really attractive for dynamic languages. LLVM doesn't give you enough access to what it's generating to do self-modifying code or code rewriting. Whereas Truffle can actually modify your code and do on-stack replacement and specialize things at runtime, which would be either impossible or very, very difficult with LLVM.
And maybe changing thanks to the what do you call it, guys? The Swift guys.
That would be very cool. I would love to see Truffle built on top of LLVM.
Oh, I see it for the G's.
Or sorry, Grail.
Does anybody worry about the monoculture of like LLVM is the best and JVM is the best and like nobody will ever investigate alternatives? I don't know. I hear a lot of that.
GHC.
Yeah. Can we have Truffle for GHC?
I mean, it's not, you know, it looks like a monoculture, but I mean, if you think about it, you know, there's hundreds of millions of dollars worth of engineering time that's been poured into this stuff.
Right.
Like, you know, GCC has been around for longer, and they even have, sometimes companies even back it, you know, they even put like 5 or 10 engineers.
Right.
But they don't have shit on like, you know, Sun, Oracle, like being like, okay, here's like 500 guys, like you just, you know, go ahead and make this stuff really awesome. You know,
so IBM put more into some of the JVM stuff than Sun did, and so I mean, lots of big companies are right. Global increase.
So it is a monoculture, but really there's nothing we can do about it.
So the idea is you can change your mind, right? Like if you design your language like for this environment, right? So like you look at Clojure, and it's like, you know what? Well, this sucks. We really can't get tail calls everywhere. But if we just don't make a standard library that assumes tail calls everywhere, we add a couple little things to our language to like deal with the fact that runtimes are constrained and haven't learned the lessons of the fucking 70s, then you know like you can still innovate even though you have to swap out your backend. And it's like, well, Clojure made a big leap forward in many areas for the designs of functional and dynamic and Lisps and whatever. And now they'll come along and say, okay, we have a different backend technology, and now we can get tail calls. And you're like, great, that's welcome.
There's a question.
So, well, it's a statement in response. So we're just going to keep tail calling each other. So the thing is that the reason everyone targets LLVM and JVM is no one wants to implement them again. They're a pain in the ass to implement all of that low-level stuff, and so the only time you ever see something like that is when there's enough effort because the existing technologies don't support it well enough. You see LLVM because JVM wouldn't support these super high-performance static languages that you really want to deal with, and then you see like V8 and all of the monkey technologies and all these things show up because JVM is terrible for dealing with super high, like low latency startup, and you need a lot of these in memory at once, and you don't want to deal with all of the JVM overhead. So there are a lot of VMs popping up. You see Dropbox starting their own Python procedure-based thing that's different than the AST and different than a tracing VM.
because they decided that it isn't quite what they want. So it's less an issue of monoculture and more people just don't fucking want to implement their own VMs. They want to implement shit on top of it.
So you said monoculture, but then he said no. So I mean, he wins, doesn't he?
Well, so there are lots of VMs out there, but there are only a few VMs that have lots and lots of work put behind them, right?
I mean,
but the other thing is not as hard as people say it is. Like you mentioned Factor. Factor was like what 7 or 8 primary contributors, and they beat V8 on a lot of benchmarks. Granted, V8's solving a harder problem, making JavaScript fast. but like it's not like it's doable. Like we know how to write VMs. It's just not that much fun.
So what's wrong with the monoculture? The thing is that it's open source now. 10 years ago, if there was a monoculture, you couldn't touch it. But now you can actually go and do things if you want to and make small changes. And that's fantastic.
The problem with monoculture is lack of competition means stagnation. So
also means industry backing. If there's a company backing it.
Well, yeah, and even they can start resting on their laurels, right? Like, I mean, SpiderMonkey was not very fast until V8 came along. It's like, oh, hello, we need some competition. It's time to start competing. They're both open source.
That's true.
But I mean, at the same time, when you look at like all the killer VMs, like you look at Hotspot, Dart, and V8, it's the same group of people. In Rail, it's the same group of people. If you want a new VM, then the key is there are 10 people on the whole planet who can help you do this, and all you need to do is hire 2 or 3 of them.
I think the really interesting point about this work is that it is a potential dart into the heart of that monoculture in a way where this is actual innovation, and the idea that you can modularly decouple the front end from the back end in this way is really interesting. And the other thing is that you don't this. I mean, how long has this work been going on for?
It was announced in 2013, I think.
Yeah, so we are getting faster and better at building VMs, and I think that this also is a death knell to the monoculture in the way that it is a language toolkit that is not designed to optimize a specific kind of language necessarily, right? So it does work better on certain kinds of languages, but they're open to opening that and working on other kinds of languages. Whereas before, if you've seen the Clojure compiler, there's all kinds of machinations in there to make a Lisp fast on top of something that doesn't assume certain things that you need to make Lisps fast. So I think that's a fair statement, and I think that it's really interesting work to see that decoupling. There's it will get faster.
Yeah,
and will get better over
the
time.
decoupling point that you made is key. That's what I wasn't seeing. I'm like, oh, we're just building it on top of the JVM. But since we have this separation where you write your interpreter in a higher level, and then you have a backend swappable even.
Yeah, and then the the ability to optimize the way that JVM and make a trade-off between later optimizations and faster startup times, for example, is something that we have never had the opportunity to do before. So I think it's fascinating work. Awesome presentation.
And again, another advantage of actually having all these different languages being implemented using the same framework is that how every single language implements, especially in the same paradigms, implements exact same additional, multiplicational, exact same ways of handling it. We could share the code. If JavaScript handles, or Python and Ruby handle addition, multiplication similarly, why duplicate the code? We could just reuse all of that. Or if you're in the same paradigm, you could reuse a lot of the specific implementations of the interpreters, which is, I think, is really, really cool, because now you open up to a lot of the different languages sharing a lot of the code base.
It makes forking much easier. So let's say you had a JavaScript interpreter that was 100% faithful and implemented all the weird edge cases, and then you're like, how much faster could I make it if I stripped all of those out? You can just do that at the high level and not worry about how does that affect the 3 levels of optimizing compiler. I think it would be pretty interesting.
Yeah, definitely. All right, well, to conclude, there is some awesome scotch courtesy of the Papers to Love organizers that I would like to share with you. So everybody's looking for this. virtual machines and compilers and languages. Thank you for coming.